Welcome back. Today, we're talking about the one thing that could seriously put the brakes on the entire AI boom. And no, it's not the algorithms, it's not the code, it's the absolutely massive, high-voltage power systems that make everything possible. So let's get into it. Okay, so let me ask you this. What do you think is the single biggest threat to the future of AI? Is it some rogue superintelligence, a lack of training data, maybe a competitor making some huge breakthrough? Well, the real answer is probably not what you're thinking. Yup, it's not about the software. The biggest bottleneck, the single biggest challenge holding back the next wave of AI is just raw physical electricity. The demand for power is climbing so fast, so relentlessly, that it is forcing a complete and total reinvention of the data center. To really get a handle on just how huge this problem is, you've got to look at the engine driving this whole revolution. NVIDIA's chips. Their product roadmap basically dictates the power demands for the entire industry. And let me tell you, the numbers are just staggering. So check this out. Right now, a single server rack running NVIDIA's latest GB200 chip is already pulling up to 150 kilowatts. That is enough to power dozens of houses. But here's where it gets crazy. Look at the roadmap. The next generation, Rubin, is going to need 250 kilowatts. And the one after that, Rubin Ultra, we're talking over 0.5 megawatt per rack. This isn't just growth, it's an explosion, and it's creating an absolutely insane engineering challenge. So with that kind of incredible demand, how on earth are data centers actually managing all this power today? Let's pop the hood, so to speak, and take a quick tour of the key parts inside a modern AI server rack. First up, we've got the power shelf. You can think of it as a big chassis that's just packed with these things called power supply units, or PSUs. They're basically the souped-up power adapters for the entire system. They grab that high-voltage AC power coming from the grid and convert it into the stable, low-voltage DC power that those hungry AI chips actually need to run. All right, next we have the PDU, or Power Distribution Unit. And really, the easiest way to picture this thing is as a giant, incredibly smart, industrial-strength power strip for the whole rack. It takes that main power feed and makes sure it gets safely distributed to every single component, from the power shelves all the way down to the cooling fans. Now, this next piece is a really crucial evolution in data center design, the BBU, or Battery Backup Unit. See, in the old days, you'd have a massive centralized room, literally a room full of giant batteries, to provide backup power for the entire building. The modern way is so much smarter. We now put a smaller BBU inside every single server rack. So if the grid goes down, the BBU in that rack kicks in instantly, keeping the servers running for those few critical minutes needed to prevent any data loss. But here's the thing, it's not just about planning for a total power outage. AI workloads are incredibly spiky. They can go from basically idle to 100% full throttle in a fraction of a second. Just look at this graph. For a few hundred microseconds, that's millions of a second, the power demand can spike to nearly double the normal load. A standard power supply just cannot react that fast. No way. And that's where the supercapacitor comes in to save the day. Think of it this way. A BBU is like a big water reservoir. It's there to provide a steady supply during a long drought, of complete power failure. A supercapacitor, on the other hand, is like a small, pressurized water tank right next to your faucet. It delivers that massive, instant blast of power needed to handle those super brief, extreme peaks. So the BBU handles the long outages, and the supercapacitor handles those split-second spikes. So this whole system, this distributed setup, it works. It works well enough for today's 150 kilowatt racks. But as we start looking at that roadmap, as we push toward 250 kilowatts and beyond, we are running headfirst into a very, very real physical wall. You have to hear this quote from an industry insider. It says everything. He's talking about the busbar, which is basically a thick slab of copper that moves electricity around inside the rack. He says that today it already weighs 80 kilograms. That's 176 pounds. To handle more power, it would need to weigh over 200 kilos. It would be too heavy, way too expensive, and it would get so hot you'd never be able to cool it. His words, this is simply not sustainable. So if you can't just make the copper bar bigger and bigger, you have to change the rules of the game. And the solution is to dramatically crank up the voltage. By going from, say, 48 volts all the way up to 800 volts, you can deliver the exact same amount of power with way, way less electrical current. And here's the key.
Less current means exponentially less energy gets wasted as heat. This isn't just a good idea, it is the only sustainable path forward.
This slide really illustrates that architectural journey perfectly. We started in the past with that one giant centralized battery room for the whole building. Today, we're in the present, with distributed BBUs inside every single server rack. But the future? The future is pulling all of those power components out and putting them into their own dedicated power rack. This new power rack will then efficiently feed high-voltage DC power to multiple server racks at once. But of course, it's never quite that simple. This high-voltage future creates a brand new challenge. You see, the traditional silicon semiconductors that we've relied on for decades just can't handle these new demands. At higher voltages, silicon becomes incredibly inefficient. It just leaks way too much energy as heat. To make this all work, we need a whole new class of materials. And here they are: silicon carbide, or SiC, and gallium nitride, or GaN. This chart tells the whole story. Just look at where these materials operate compared to plain old silicon. They're designed for much higher voltages and frequencies. And what that really means is they allow for power conversion that is over 98% efficient. These materials are literally the key that unlocks this entire high-voltage revolution. And you know what happens whenever there's a fundamental tech shift like this, right? A massive new market is created. Projections show the annual market just for these advanced power materials and AI data centers is going to grow into the tens of billions of dollars by 2030. This is a huge, huge opportunity for the companies that can master this new technology. So this revolution isn't just about technology. It's completely reshaping the entire supply chain. It's creating intense new competition and a whole new battleground for who gets to build these absolutely critical systems. For years, this market has been dominated by a few big, established players. But now, the cloud giants, think Amazon Web Services, are actively shaking things up. They're bringing in new challengers to the table, and they have two big motivations. First, foster competition to drive down costs. And second, accelerate innovation. For example, they're pushing suppliers to adopt newer, safer battery tech like lithium iron phosphate, or LFP, for those backup units. It's all about creating a more resilient and more competitive supply chain for everybody. So what you should really take away from all this is that the race to power AI is just as critical as the race to build the AI models themselves. We are watching a foundational shift in power engineering, driven by the simple laws of physics, and it's creating a multi-billion-dollar battleground. The real question isn't just, can the grid keep up? It's, who is going to win the race to build the revolutionary systems needed to deliver all that power?